Welcome everyone to this online Spintronics seminar number 113. Our speaker today is Professor Cheng Gong from the University of Maryland. Professor Gong received his PhD in 2013 in material science and engineering at the University of Texas at Dallas. Then from 2014 to 2019, he was a postdoctoral fellow at UC Berkeley, where he pioneered the experimental discovery of the first two-dimensional magnet. And then since 2019, he has been an assistant professor in the Department of Electrical and Computer Engineering at the University of Maryland at College Park. His research group focuses on two-dimensional quantum materials and devices. Professor Gong is a recipient of IUPAP Young Scientist Prize in Semiconductor Physics in 2020. And in 2022, he won the University of Maryland's Invention of the Year Award and the ACS Maryland Chemist of the Year Award. So his talk today will be about efficient control of two-dimensional magnets. And with this, I'll hand it over to you, Cheng. Please go ahead.
Hi, let me turn on the laser point. Right now, looks like it's cursor again. Okay. Thank you, Korea, for the introduction. Thank you, Korea, and also Shen for invitation. Also, thank you all for being here to listen to my talk. My talk today is about efficient control of 2D magnets. Specifically, I will introduce electrical way and optical way to control 2D magnets by hopefully an efficient way. So I think people here are familiar with this concept of 2D magnets, especially for this online Spintronics seminar. The audience should be in a similar field. Maybe some of you are in the traditional thin film Spintronics, not exactly in the 2D field. So I will begin this talk in this way, give a background, especially summarize a major effort in trying to find the 2D magnets. So introduce one piece of my early work during postdoc for the experimental discovery of 2D magnets. So that can give some, especially those audience, a good sense how we work on and handle the 2D materials. And then I move on to introduce the electrical control and optical control of 2D magnets. Even though many times in papers we saw those claims like 2D material is so thin, so very easy to be controlled. On the one hand, it's true, many ways that cannot be altered, the bulk material property can be easily used to alter the 2D material properties. But on the other hand, the efficiency may not be that high. So we'll give some analysis and hopefully revealing some fundamental insight on why it's not so easy to realize the efficient control, and present later on, present several our experiment progress for these goals. So for 2D magnet, we know 2D materials have been there many years, since about 20 years ago, about discovery of graphene in 2004. And from then, actually, there has been a lot of ongoing research trying to find magnetic 2D materials. There are several mainstream strategies to trying to find 2D magnets. The first very mainstream effort is based on defect engineering. No matter it's graphene, molysulfide, such non-magnetic 2D materials. Basically, you can create a defect to easily introduce local magnetic moment by either add something here or take away some element from the lattice. So either way, by adding something or taking away something, you can create the local spin moment. But it's very hard to arrange this spin ordering, this moment in a long-range magnetic order. So until even recently, I did not see a consensus in the field that using this strategy has ambiguous find to the magnetism. The second way is very smart method by magnetic proximity effect. Basically, for whatever non-magnetic 2D materials, if you can prepare them together with traditional magnetic thin film with a clean interface, by large chance, you can use the interfacial spin wave function overlap to magnetize or spin polarize the electron in the originally non-magnetic 2D materials. As you can see, this is a way, almost a universal way to induce spin polarization in non-magnetic 2D materials. This is an extrinsic way. We certainly know this, for example, graphene here, magnetism does not directly originate from the exchange interaction in the pi electrons in graphene. That's not the case. And for device application, you probably need to carry the whole stacks to fab the devices. So the third idea is very smart. By finding those materials who has the flat band, so you can have a large density of states within a very narrow energy window. So that can cause the so-called stoner instability. That's why in some metals, elemental metals, we found the magnetism long-range mag order. It's very hard to find those kind of insulators. So for example, this electrically biased bilayer graphene, you can open a gap, small gap, and then you can have a flat Mexican head flat band here, or highly p-doped gallium sunlight. But anyhow, it's not easy to really get that materials and exactly prove that region. And several years ago, with the discovery of this model insulating state and superconductivity in graphene system, especially bilayer graphene or trilayer graphene interfacing with hexagon boron nitride, people found that flat band and also demonstrated the ferromagnetism there. What we used was very straightforward method. Basically, there are some van der Waals materials already in nature or by synthesize. For example, chromium germanium telluride is a bulk crystal and layered structure. And you can exfoliate them into very thin layers. And in bulk, it already has the magnetic property. It's not like the magnetic doped semiconductor. So it's not magnetic impurities, but actually part of the crystal. So for this one, if you look at the magnetic property, it's a ferromagnet with about 60 something Kelvin Curie temperature, and you have a very small hysteresis loop window, but you have it. So if you zoom in, you will see it here. So you can use a small field to saturate. Interestingly, if you apply this magnetic field along the crystal plane, AB plane, or perpendicular to the plane, you will find actually there is an easy axis anisotropy, even though it's not so huge, but you have outplane anisotropy. I emphasize this because this is really important. If such a system, 2D magnet, if you don't have such an easy axis anisotropy, you will not break up the continuous rotational symmetry. So that will easily actually, without such a continuous symmetry breaking, any finite temperature can easily excite those spin disturbance and destroy your order. So this is a classical Merwin-Wagner theorem. As you can see, there is a condition for those isotropic Heisenberg model. You will never see those finite temperature long-range magnet order in 1D or 2D system. So, but if you have an easy axis anisotropy, you can have it. So classically, you can imagine that if you have an easy axis anisotropy, in order to randomize the spin, you need to overcome the anisotropy, right? But from the spin wave excitation, spin wave picture, you can also have this understanding. This kind of analysis has been presented in these two papers in detail if you want to read more. But you can see if you have a 2D system or modulated system, let's start from here. And if you don't have any anisotropy, easy axis anisotropy, you don't have any gap, spin wave opening, gap opening. So actually, at any finite temperature, you can easily excite a lot of density of state. Plus the divergent statistics here, you will totally actually destroy the magnet order. And when you have some layers, you will have such a step function, but still there is an onset of a lot of density of state with a gap. So gap here is a P that can sustain your material's long-range magnet order to be against the finite temperature thermal agitation. So that this CGT has the easy axis anisotropy, so it's good. We probably can have the long-range magnet order. And for those people who are not into the field, we usually start from such a silicon wafer, cut into like millimeter size, several millimeter by several millimeter in size. usually half millimeter in thickness, and then you exfoliate a lot of flakes on the surface. And under optical microscope, you can find that one flake, which is very thin, which is what you need. And so here is the key. You can see the 2D materials volume difference with the whole substrate volume difference. That's probably 10 to 10 or even 10 to 12 difference. So 2D materials volume here is almost negligible. If you threw the whole wafer into the magnetometer like SQUID or VSM, see some tiny hysteresis loop, it's very hard to conclude where this hysteresis loop comes from. Maybe very likely from the impurities in the substrate or at the interface or on the edges of thousands of different flakes. So we need an area selective method to just approve this flake rather than the whole materials. So what I used before is magneto-optical Kerr effect. You can see if you have a magnetic thin film, and if you shine the linear polarized light, the linear polarization is represented by this arrow. And upon reflection, this linear polarization plane will have a rotation. That's because of this spin and orbital coupling. So you will have rotation. By keeping track of this Kerr rotation angle, you can keep track of the magnetization as a dependence on, for example, sample thickness, temperature, magnetic field. You can see here, this method can just precisely select that micrometer scale sample to prove that specific or individual flakes. It will not pick the whole substrate millimeters size substrate signals. So this is the atomic thing CGT exfoliated before on silicon oxide and silicon, and when you put this one into the cryostat to cool down, you can see there is a clear emergence of a co-rotation angle here for the 2-layer region. At 40K, you see the signal is already gone, but the 3 layers still have very clear signal. So this indicates a clear thickness-dependent TC. The thicker sample may have a higher TC. So then we do the systematic study for different thickness, 5-layer, tri-layer, 4-layer, 5-layer up to bulk. For each one, you scan, you measure the temperature-dependent co-rotation. You can then extract the thickness-dependent TC. So you indeed have such a dimensionality effect that has been observed many times in the traditional magnetic thin film. That indicates in this 2D system, there is indeed a very strong thermal fluctuation that causes the reduced TC. This is also one fundamental reason why it's so hard in early days to observe 2D magnet. Samples sometimes are not so air stable, and signal from the atomic thin micrometer size sample is also not as strong as a bulk crystal. So there are many challenges associated with the observation of magnetic signal from that small flake. After looking at this temperature-dependent data, we usually will check the hysteresis loop to prove this is ferromagnetism. So as you can see, for another flake, we see this hysteresis loop very much like its bulk counterpart. So it's ferromagnet, but with a very small window. The remnant saturation is only about 5 or 8% of the saturated magnetization. Here, the key is whether we have zero magnetization, remnant magnetization or not. That decides whether this is a ferromagnetism or not. So by looking at these 2 data, actually these 2 data are extracted from a scanned co-rotation image. You can see when I withdraw the field from positive field or negative field, the remnants are there, non-zero, opposite in sign. So this is a clear evidence. This is non-zero remnants that shows this is a ferromagnetism. So these 2 part of data, temperature-dependent data, magnetic field-dependent data, clearly confirm this is a 2D ferromagnet. And now I think you all see this field is really rising up quickly towards different fronts. So for the next part, I will introduce the electrical control and the optical control. Especially for electrical control, we have many slides here, and optical control, we have a relatively small number of slides. For electrical control, let's do a little bit of analysis. You know, people, okay, when we talk about control, of course, it relates current control and the voltage control. Ideally, people like to use voltage control because that may not cause any dual heating. and energy efficient. It's energy efficient. So for voltage control, when you do experiment, you know there are roughly two types of commonly used control. One is you apply a electric field, pure electric field. That's the electric field control. The other one is you use a transistor structure. You apply the gate voltage on the source and drain electrode with respect to the ground. So you have electrostatic doping control. But either way, we will see actually it's very hard to get efficient control, because if you use electrostatic doping control through silicon oxide, likely you can only control the carrier concentration between 10 to 12, maybe close to 10 to 13 carriers per centimeter square. But each surface have 10 to 15 atoms usually. So that means for each atom, surface atom, you only modulate the electron concentration by 0.001 electron to 0.01 electron. So that's fractional. Of course, some people will say maybe use the ionic liquid. That's very complicated. Sometimes the ion can easily penetrate there and distort the atomic structure. That's out the scope of discussion here. The other one is electric field control, but you cannot, usually the externally applied electric field is very small compared with inherent crystal field. And if you want to apply a larger field, probably you will break up the substrate or some materials in this device stacks. So usually the applied electric field maybe just like 1,000 times smaller than the inherent crystal field. It's very hard to change the crystal field by external field. So you can see both ways is not easy. And so, but you sense already, if we can change the electric field, crystal field, that's very good. So I borrowed the concept from multiferroic community. If we have such a heterostructure multiferroics like 2D CGT, ferromagnet, 2D indium selenide, 2D ferroelectrics, you can put them together. And then when this ferroelectric will allow you to use a small voltage to flip the ferropolarization. Ferropolarization flipping means the ions are moving. Once the ions are moved, actually that means the interfacial crystal field can potentially be largely altered. So it's not only an electric field or is an electronic injection, but there is an ionic bonding alternation. So this DFT paper indeed showed when we flipped ferroelectric polarization of indium selenide from up and down, and that links the in-plane ferroelectric order as well. But here we are only talking about the out-plane order, so up and down. Actually, the magnetic anisotropy of this 2D CGT is bent between in-plane and out-plane. So that's not a small change. It totally bent the anisotropy. So for some people who are not familiar with such an interfacial crystal field, you know such a bonding will really affect it. So in a previous science paper I reviewed, actually you can see when 2D materials contact with whatever other materials, there are many mechanisms to easily change the property of this 2D magnet. We will not go into every mechanism here, but I will just use one very simple experiment to demonstrate such an interfacial crystal field can easily change the anisotropy. So here you can see there is a few layer FGT is around 8 to 10 layers. I remember it's 8 nanometers, so it's not so 2D. But when we put one monolayer molysulfide to cover part of this 8 nanometer FGT, you actually can still see in this 2 region at a certain temperature when we measure the hysteresis loop. We sample several different positions here and different positions here. You do the hysteresis loop, you can get the coercivity. You find the one layer molysulfide covered region has around 180 Gauss, smaller coercive field than the bare FGT. So you can see such a one layer sample is enough to change the coercivity, which experimentally suggests the magnetic anisotropy change. You can imagine if this FGT is not 8 nanometer, but for example, like 2 nanometer, or I believe the interfacial effect is even stronger. So anything, you put a ferroelectric material there, it of course can change the anisotropy of that material. And when you polarize the field of polarization, you will have a polarization dependent interfacial crystal field. Of course, you also have interfacial transfer, interfacial dipole, those things. But interfacial crystal field should be a main factor you need to consider. So it's possible. And then, okay, I will move on to introduce the second piece of theoretical work, how to realize the high efficient electrical control. Usually when we mention high efficient electrical control, we are interested in two parts. One is, can I use a small voltage as a small, little requirement on the energy input. The other one is, how can we realize a big controlling effect? So we can use a little bit of energy as input to realize a huge controlling effect. So the first part of work using multiferrite is trying to focus on how to use small voltage. And here the second part of work is focused on how to maximize the controlling effect. You have many ways to define the controlling effect, but one very popular way is, how can we control the spin polarization between 0% to 100% spin polarization. So this part of work is focused on that goal. Now you have a 2D ferromagnet, you have another 2D ferromagnet, but they are coupled in interlayer antiferromagnetic coupling. So this is called A-type antiferromagnet. If you look at the one layer alone, that's ferromagnet. So spin up and spin down band are split. If you look at the other layer alone, it is also ferromagnet. But if you put them together, they have a interlayer of antiferromagnetic coupling. So as a whole, it does not give net magnetization. You have the spin up and spin down, this band splitting in two layers in a reverse way. So you can imagine now, if you apply an electric field across these two layers, the two layers will feel different electrostatic energy, right? They have the different potential. So you will lift up one energy level, the energy level in one layer, and push it down the energy level in another layer relatively. So in the end, you will merge one spin polarized band and open up the spin polarized band of the other spin. So you can imagine, if you flip the electric field, actually you can push the red band here to be merged at Fermi level and the blue band be opened. So anyhow, you can see we form a special material that's called half metal. So all the spin polarization, so all the conduction electrons now at Fermi level are from one spin, and the other spin polarized band are still insulating. So you can leverage this 100% spin polarized Fermi electrons to realize to develop the spintronic devices. So you simply build such a bilayer A-type antiferromagnet in based transistor. You can use a vertical voltage, gate voltage to create the half metallicity by applying voltage above this crystal voltage. So you can use positive voltage, negative voltage to push spin up and spin down electron into the half metallic state. So you have a switching function. You can reverse a spin polarization, a carrier spin polarization. It's analogous to silicon transistor. You can switch on and off, but here is the silicon transistor is a reversal between electron and hole. Here is a reversal between different spin polarizations. So as you can see, this part we use the electrical control of A-type antiferromagnet to realize 100% spin polarization. But you probably need a larger voltage, so it's not energy efficient as well. And so we will combine the first two sorts. We have this ferroelectron material to allow you to use a small voltage. We have this A-type antiferromagnets to potentially allow you to realize the 100% spin polarization in half metallic state. So in such a heterostructure, we use DFT to calculate the band alignment. Again, it's pretty much like what we studied before. You know, again, in the beginning, you just have this A-type antiferromagnetic state, but we have a ferroelectric polarization, effectively just like the externally applied electric field. You can push it down and lift up the energy levels, and you can cause the Fermi level to across this spin, let me use a loose word, spin red band and spin blue band. So you can have again a multiferroic spin FET. So you have such a ferroelectric A-type antiferromagnetic stacks, and you can use voltage here. Given the presence of the ferroelectric materials, potentially you can use just a small voltage to control the half metallic state for the control of 100% spin polarization. So for this, you can see the third work is totally a combination of the first two ideas. So first one is focused on ferroelectric control to allow us to use a small voltage. This one focused on the output. Can we create half metallicity? And then this one is a combination of the two to use ferroelectric to enable small voltage control and target at half metallicity for 100% spin polarization control. These are all theoretical work. So I will move on to two pieces of experiment we did on similar topics. It's not easy to fully demonstrate the half metallicity because there is always been depolarization process, and at finite temperature, you also have the excitation of somewhat excitation of the spin minority carriers. So it's not easy to cleanly demonstrate 100% spin polarization. But anyhow, this at least provides a possible pathway. So here is a piece of work. I focus on the development of 2D ferroelectrics. You can also use the traditional ferroelectric for those kind of visionary work. But many traditional oxide ferroelectrics, if you have it very thin, because right now you want to use small voltage, so you need to let the material to be thin. The thickness times the coercive field is equal to the switching voltage. But when it is thin, many times the defect will cause very much the substantial leakage current. So 2D ferroelectric potentially are better in terms of electrical insulating with minimum amount of defect. So, but when I develop them, we find something very interesting here. It's not related to magnetism at all for this piece of work, but I'm very proud of this work. As you can see, we built a ferroelectric tunnel junction, traditional metal chromium, and 2D ferroelectric copper indium phosphor sulfide. In the experiment, it's about 3.5 nanometer in thickness, just about 4 layers, and then graphene as a bottom electrode. So you have a asymmetric electrode. That's the key for ferroelectric tunnel junction. So you can imagine they have different work function, and then you can use the ferroelectric polarization of this spacing layer to either reduce or enlarge the difference of these two chemical potentials, and you can realize the so-called smaller or larger tunneling barrier. And so compared with the traditional ferroelectric tunnel junction based on oxide, there are 3 advantages here, potentially leading to the very huge tunneling electrode resistance we observed is 10 to 10, at least 4 orders of magnitude higher than the traditional oxide-based ones. And they are at room temperature. Our demonstration are at room temperature. So the first advantage is, as I said, this is 2D ferroelectric, but with minimum amount of defect. So the gap, the band gap for tunneling is very clean. For those defective oxide, you will have a messy band gap. So that will actually kill or damage the on-off ratio. The other one is there is no Fermi level pinning between this insulator and this electrode graphene. If you have a Fermi level pinning, that will also weaken or even negate the ferroelectric control of band alignment. The third one is the asymmetry between these 2 electrodes are really large. Conventional 3D metal and 2D metal, and especially these ones, energy level chemical potentials can be easily controlled. If you have 2 similar conventional metal, chromium gold, chromium nickel, whatever, such a difference is not as large as these 2. So this electrode asymmetry is another reason. So for such a ferroelectric tunnel junction, we easily routinely demonstrate 10 to 9 on-off ratio when we polarize the ferrite layers, the resistance is changed by 9 orders of magnitude. And sometimes, you know, I said I encourage students to try just put one layer of TMD, which is also gapped system. Let's see what will happen there. And sometimes they observe 10 to 10 on-off ratio. So in order to prove this is true, rather than a sample variance, we design such a well-controlled experiment. As you can see in this device, you have the same substrate, of course. You have the same graphene flake, and you have the same CIPS flake. You have same chromium gold electrode. The only difference is between CIPS and graphene, another device have one additional monolayer transition metal dichalcogenide. We tried the moly sulfide and also tungsten selenide. And here you can see so this is a well-controlled experiment. The two devices, the only difference between the two is the presence of one monolayer transition metal dichalcogenide here, moly sulfide. So you can see the on-state current is not changed much, but the off-state current was further surprised by 10 times due to the presence of such a gapped semiconductor in between CIPS and graphene. So this shows a layer by layer engineering of the electron tunneling pathway is really layer by layer. And this is physically very intriguing. And also it gives even enhanced on-off ratio. So that goes to 10 to 10. As I said, this is at least 4 orders of magnitude higher than the best of the electrode resistance for oxide-based ferroelectric tunnel junction. And again, this is demonstrated at room temperature. Another small add-on, you have such a ferrotunnel junction, and the given graphene is already on silicon oxide silicon chip. So spontaneously, we can think about doing an experiment, use a backgate voltage to tune the energy levels of graphene and to fine tune. You cannot control by 10 times simply by working on graphene, but anyhow, you can fine control the on-state current in an asymmetrical way because the graphene's initial doping level is not intrinsic, it's not at direct point. So depending on its initially N-type doped or P-type doped, you have such a asymmetrical V-shape control of the on-state current. So this is very interesting. And go back to what we discussed about ferroelectric control of 2D magnet. This is another piece of experimental work. You can see here is a 2D CGT, chromium germanium telluride, and we deposit the polymer ferroelectric PVDF TRFE, and then use transparent electrode ITO, so we can apply voltage, but meanwhile, we can still use our optical way to prove the magnetic property of these 2D magnetic materials. So as you can see, this is what I mentioned. When you flip the full ferroelectric polarization, for example, this PVDF TRFE, you are actually having different interfacial configuration. Here, you can see you have hydrogen and fluorine in direct contact with the 2D magnet. But in another polarization, you only have fluorine. So this is what I said, the ions are moved, the interfacial bonding and the crystal field is totally changed. So that a crystal field change, of course, will due to, we know the magnetocrystal anisotropy arises from spin-optical coupling and the crystal of symmetry. Once you change the crystal field, you are changing the different orbital moments contribution. And when they couple with spin, that will change the magnetic anisotropy. So for such a, you can see in figure D here, you have 2 layers, you have 8 layers, just using these 2 regions. For this 8 layer, that's a SIC CGT. When we apply positive, negative voltage, you do not see a clear change in the hysteresis loop. But for that 2-layer region, you can see a clear opening and the closure of the hysteresis loop. By keeping track of this remnants or coercivity, we have the voltage-dependent coercivity or voltage-dependent remnants. It's non-volatile. So certainly this is because of that ferroelectric polarization. Here we summarize the effective voltage only on the ferroelectric layers, because here you can see a lot of voltage is actually wasted through silicon oxide. So you can use a capacitance model to calculate, and the voltage drop on the multiferrite itself is only about 5 volts. 5 volts, 50 nanometer PVDF-TIRP that's equal to around 100 millivolts per nanometer. This is normal as a switching coercive field for PVDF-TIRP. Later on, we also redesigned the experiment by removing the silicon oxide substrate. So we directly used also around 5 volts to flip the ferropolarization and the magnetic property. And we observe the same non-volatile control. So this is certainly the multiferroic effect based on the ferroelectric polarization dependent magnetic properties. But anyhow, for that vision, for that half metallicity is still on the way. As I said, there are really a lot of challenges, but you can see such a ferroelectric control of 2D magnet could enable many things. So last part, I will move on to introduce optical control of 2D magnets. This topic has been there many years in traditional thin films. People just shine a strong laser, ultra-fast laser pulse, usually on the order of 10 to 7 microwatt per micrometer square to flip the magnetization. There are many mechanisms to allow them to control. One is the so-called inverse Faraday effect. You use the effective magnetic field of that strong circularly polarized light to flip the magnetization. The other one is a photo-induced doping, a strong laser, so you probably can inject 10 to 13 or 14 carriers per centimeter square. The other popular one, mechanism is magnetocircular dichroism. Basically, you have materials, you have spin-off domain, spin-down domain. When you shine your circular polarized light, one spin polarized domain will absorb the light more than the other spin polarization. So that will be heated up just above TC. The other one, absorbing less light, will not be heated up to be demagnetized. So the heated up one becomes demagnetized, and given this is ultra-fast laser pulses, so between pulses you have a long window, and it will cool down. And when you cool down, you have 50 by 50% chance to go to either original spin or flipped. So, but laser pulse keep being incidented on this sample, and finally your sample is flipped. But by either mechanism, you have to use a strong ultra-fast laser on the order of 10 to 7, 10 to 8 microwatt per micrometer square, sometimes 26, depends, but it's on that order, similar order of magnitude. So here, what I did is totally different from this traditional magnetic switching. I'm not working on switching here. We know for a 2D magnet, if the spin configuration are changed, that means different properties. Sometimes the changing is even between topological spin texture or non-topological ones. That's even a marked difference. But anyhow, spin configuration, if you change it, that means essentially you change it to another materials. Even though typically we only consider material as the atomic configuration, but when electron spin are addressed on the atom's crystal structure, if you can control them, of course, you can also control the properties. So here I'm trying to control the domain behaviors, the domain formations on the 2D magnets. We know if you have a 2D FGT here, itinerant ferromagnet, if you cool them down in darkness, which is usually what people did, and at room temperature, it's non-magnetic phase. Cool it down across TC, like this 4-layer sample. TC is about 140 to 150 K. You cool it down, likely you will form this multiple magnetic domain. This is reflectance magnetocircular dichroism. You can understand the different color as different magnetic domain orientations, spin up and spin down. So when I heat this one up to room temperature, become demagnetized, repeated the cooling process, but shine a very low power. As you can see, only 13 microwatt per micrometer square. And you can see when it's cooled down to 100, I forgot this is 100 or 110 K, but clearly below the TC at 140 or 50 K. And it forms multiple domain, but you can see the domain size is enlarged. And the blue area occupies a little bit more, over 50%. If I heat it up to room temperature, demagnetized, and repeat the same process, by shining the same linear polarized light at the same power, you can see the similar domain enlargement effect. But this time the yellow area occupies more. So you can see linear light is efficient in control the domain formation, but you cannot deterministically control spin up or spin down in the end will dominate. Well, this is not surprising because this linear polarized light can excite unpolarized electrons in the material. And so that triggers us to do another interesting experiment. If we cool the sample, but during the cooling process, we shine the circularly polarized light, you can see just about 20 microwatt per micrometer square, you can actually control the formation of almost a single domain. Some part are pinned there, it's very hard to flip. But anyhow, you can see the single domain formation deterministically controlled by the circular polarized light. So you can use spin up, spin down to control the the magnetization spin up or spin down domains. This is a deterministic control. I think the mechanism is very interesting because any practical 2D magnets, it's just like, for example, graphene. You probably remember, graphene is not ideal 2D material. You always unintentional strain, roughness, unintentional doping. Early days, the direct Gong. At direct Gong, you should see 0 density state and 0 conductivity, but people never saw the really 0 conductivity. And so early days, people actually found there is always non-uniformity induced electron hole puddles. Even overall graphene has 0 density, but it will break up into many different regions. Some have a small amount of electrons, some area have small amount of holes. The total number can be canceled, but you have such a patches, electron hole puddles, and that can form the percolation network for conductivity. So 2D material are never perfect. For 2D magnets, it's the same. You always have unintentional doping, unintentional strain, and those kind of roughness. You can imagine the different regions may have slightly different TC. So, for example, this red area have relatively higher TC. The other area maybe have a relatively lower, maybe just a 0.1 K or even smaller or even larger, 0.5 K. We don't know, but you have such a non-uniform TC distribution. So when you cool this sample down to low temperature, from high temperature across TC, you can imagine those highest TC region will go into ferromagnetic phase first. And given they are decoupled by this non-magnetic phase in between them, so they can get into the ferromagnetic phase randomly. Of course, if they are close to each other, they probably can feel a little bit of stray field. But stray field as a dipolar interaction actually will push them into anti-ferromagnetic, kind of anti-aligned spin. So you will have the formation of multiple domain. It's not simply by the ideal case. You consider the competition between exchange interaction, anisotropy, and dipolar interaction. But practically, you have different patches, so you will get into multiple domain because they are weakly or even not interacted with each other. So that's why you can form multiple magnetic domain. And now, if you shine the light like we did, circular polarized light, you can see here at a T temperature above TC, you have the non-magnetic phase, but you already injected in the material many spin polarized electrons everywhere. They are just like tiny magnet implanted there. And then when you cool them to TC of the other regions, they will, the highest TC region, they will follow the injected spin by exchange interaction. So you can have single domain formation. This is pretty analogous to the CVD growth of some flakes like graphene on copper. Many times you will end up with polycrystalline graphene or molysulfide. You have many domains. But if you control the nuclei, the initial nuclei, and people usually use this way to guide the formation of a single crystalline 2D materials. So this is very analogous. So as you can see, okay, I will stop here. You can see as a summary, first part we presented the early days work experiment discovery of 2D magnet. And then I show the electric control of 2D magnets with a focus to use small voltage to control the large magnetic property change. So there are 3 theoretical work I introduced and 2 pieces of experimental work about our development of 2D ferroelectric and ferroelectric tunnel junction, and also 2D ferroelectric control of 2D magnets as the so-called heterostructure multiferroics. And in the end, I show the optical control. This is not a traditional way of optical switching, but it's optical training of the formation of spin domain configurations in 2D magnets. The power is really low, just like 20 microwatt per micrometer square. So with that, I will conclude my talk here. I did not mention those collaborators in the early works. I just mentioned those recent collaborators on the work at UMD presented here. We also have a lot of collaborations. Those work I did not present here, so I did not include a full list of collaborators due to the limited space. Just to cover those works I covered, and that's those collaborators. So I also give the thanks to the several different funding agencies to support us to conduct the exciting research, and 3, the postdoc, Dr. Cheng Wang, and the 2 students. They are really diligent, hardworking, and smart. Thanks for their great effort to have this kind of very interesting outcome progress. So with that, I will stop here and welcome any questions.
Thank you very much, Cheng, for this very interesting talk. We can use the reactions buttons to thank him. We can take questions. Please use the raise hand feature in Zoom. If you're in Twitch, you can just type your question in the chat box and I'll read it for you. So questions, please. Ren, Cheng, please go ahead.
Hi. Hello. Hi. Thanks for the very interesting talk. So I have just a question about the really significant tuning of the band structure to create a semi-metal by the electric field. I was wondering what is the mechanism of the next slide, maybe right, this one, yes. So what is the mechanism of this highly significant electric control of the band structure? How can one just change the band structure and overcome the gap to create a half metal by a moderate electric field? I mean, what is the mechanism here? And also a related question. So 1, 2 layers on top of each other. So then will the electron hopping between the layers, or the hybridization of the band structures from the 2 different layers also contribute to the change of the band structure?
Okay, that's a good question. As I introduced the concept here, this part of work, we did not aim at using small voltage to realize this effect. So basically the mechanism here is you have an electric field, you have the different electrostatic energy for the 2 layers. So one will be pushed down, one will be lifted up. So in the end, you will always merge them, but you may need a large voltage. So that's why we move on to the 3rd piece of work by including ferroelectric materials. So we are not only applying the external electric field, but the ferroelectric polarization here can help you, because the ferroelectric material with the inherent polarization can enlarge this field effect. So with that, we hope to reuse a relatively small voltage to reach the half metallic state. The second part of the question is about whether they will hybridize.
Yes.
Yeah, as you can see simply from the band structure like this, we did not consider that part because it's just a Van der Waals gap. Of course, there is wave function overlap. So I think in practical devices, of course, the electron may easily hopping between layers. But the key, I think key here is close to Fermi level, no matter in this layer or this layer, you have the same spin. Even though this one, for example, get excited to here, it's still the same spin. You know, we are okay if certain probability of interlayer hopping is there, as long as it's not depolarized. You know.
Okay, because generally one could anticipate that there's a strong hybridization of electron orbitals from different layers, which may contribute also substantially to the formation of the two-layer band structure. So yeah. I was just asking, so I have no idea. I mean, what
I think you're
is a
right.
strong effect?
Even like two more molysulfide more layers, I think the single layers quasi-particle band gap maybe around 2.2 or 2.3 eV. I mean quasi-particle band gap. And when you merge them, they will have at least another 0.3 to 5 eV reduction. But so even though, I mean, there is a reduction, like I put the picture here, there is a reduction. You can imagine the overall, just the size becomes smaller, but this relative spin orientation still holds, right?
Okay, so the electric field here is out of plane.
Is across this two plane. You can see we plot it in this way. Yeah.
I see. Okay, thank you.
Yeah.
Thank you. Zhuangyan Fu, please go ahead.
Yeah. Thank you for your talk, Cheng. Yeah, regarding your experimental work on the multifarious control of GPT, the natural electronic one. Can you go to that? So I'm wondering, have you ever do a control on any other one? Have you do a control experiment just without the ferroelectric layer? I mean, it's maybe just like you are using a pure gate voltage, you can have this hysteresis loop open and close, and just even without a ferroelectric laser. Is that possible?
As said, pure electric field, in principle, can cause effect. I think in 2018 there are at least 5 good papers published in high-profile journals on electric control of either chromium triodide or ion germanium telluride or chromium germanium telluride. But anyhow, in those work, in that year, I did not see the focus on coercive. In chromium triodide, the people observe the switching field, but that's not, you know, you have a flipping field at around 5,000 or 6,000 Gauss. You can control it. But here is whether you have non-volatile control. That's a very key difference. Voltage, of course, will be you can, voltage is not so effective in terms of changing the crystal field, but when you apply voltage, if you count them in, that certainly can still effectively change the crystal field to a small degree. So you certainly can have that effect, either voltage by electric field or through voltage by electrostatic doping. You can always control. But two things: one is the efficiency, the other one is not volatile, non-volatile.
Yeah, I see. Yeah. The ferroelectric layer may like help to retain the magnetic state of that, right? Okay.
Right.
That's good.
Right.
Okay, thank you.
Okay, I don't see further questions at this time. So we're going to thank Cheng again for this very interesting talk, but I would invite those who would like to stay and continue the discussion off the record. Please feel free to hang on and turn on your camera just after I stop the recording.